Good morning, good afternoon, good evening, wherever you're joining us from. I'm happy to present on behalf of OPAL-RT on advancing off-highway vehicle autonomy through simulation. So before we get started, just want to remind you to give us a follow on LinkedIn at OPAL-RT Technologies and to check out our upcoming webinar schedule as well for Power Hill and our Innovation and BMS series, parts 2 and part 3. First up, so I'm Thomas Kirk, or Tom, Market Development Manager at OPAL-RT Technologies, just working on bringing solutions to the market and making sure we ensure your needs. And I'm here today with my colleague, Valentin Puyfourcat, a field application engineer who will be showing you a demonstration a bit later in this webinar. We're going to start off with an introduction, an overview of 4D Sim, which is a simulation tool we are offering, some applications, then the demonstration, followed by a question period. I remind you that you can use the Q&A in the Zoom meeting. Questions will be answered either live or at the end of the webinar. So if you're not familiar with OPAL-RT, we are a company that provides simulation tools to help you build better products. So whether that's through research, innovation, or just bringing your product to the market, we're there for you. So we have a host of other products that serve several markets, and we're an international company. So we started off in Canada, out of Montreal, but now we've become international. We have offices across most continents. And as far as our autonomous vehicles office goes, it's based out of France, but me and Valentin were actually based out of Montreal. So you can count on support globally. As I mentioned, we work across different industries. So we have roots more in the power systems, energy side of things, but we also work with automotive companies, off-highway companies such as Caterpillar, John Deere. We work with many institutions in research, whether academic or research laboratories, and we also have a large presence in aerospace. So let's hit autonomous driving. The key of what OPAL-RT wants to provide in this sector is simulations. So innovators in this field are developing perception and fusion and driving functions that control actuation that get fed to vehicles or robots. So those vehicles and robots need to navigate an environment, and that environment is captured via sensors. So fundamental in our simulation is the ability to provide the sensing environment and vehicle simulation. So I'm not going to go into detail during this webinar about these aspects, but I'm going to focus more on the blue. What makes off-highway vehicles different than road vehicles? Well, obviously they look a lot different, but clearly terrain. So you're not just on a road or a highway. You don't have necessarily an urban environment with landmarks. You don't have lines on roads. So you need to navigate all sorts of different terrain, whether it be sand, mud, dirt, fields, you name it. Dynamics, we're not talking about just car dynamics. These vehicles are more complex. There's potentially a soil interaction with the wheels that needs to be modeled appropriately. We may have tracked wheels, which is fundamentally different than what you see on on-road vehicles. And finally, there's a whole other element of functionality. You might actually have to integrate, tow, or push different types of machinery, or have integrated robotic systems, such as arms, which could be more complex to operate and change not only the dynamics of the vehicle or robot, but also have its own autonomous function. On that note, the applications in this field are varied. There's a lot of different things that people in this sector are working on. So obviously, vehicle navigation localization, being able to direct a vehicle through the field of operation appropriately, and also plan for that. There's actual autonomy of subsystems and functions. So whether that's a robotic arm, an implement, an excavator, or in some cases, more focused on data. So detection and mapping applications. And finally, there's also this whole sector of collaborative robots. So assistants to humans, whether it's in a field or a warehouse or anywhere else where that may be of aid. So there's a lot of different work happening in this area. So what are the requirements? There's several. Well, one of them is for sure a 3D environment where you can actually simulate the physics, vehicles, actors to represent the scenario, your scenario. We need to be able to simulate sensor models as being shown in this video, especially with high fidelity to replicate reality. And we need to obtain ground truth data. So when we're working on machine learning algorithms, that ground truth data is extremely helpful in training those algorithms. We need connectivity. So there's different elements of connectivity that may be required depending on a project. Maybe we want to connect to software. Maybe we actually want to integrate directly to some code. We want to connect to ROS. We might want to connect directly to other hardware in the loop, ECUs. We might actually need co-simulation. Perhaps this simulation is not the only simulation that is required to make an application work. Maybe we need to connect to other tools. These are all important. And finally, especially when considering off-highway vehicles, we need to be able to import terrain. So what if we have a large landscape? We don't want to have to model that from scratch. We want to be able to bring that into the simulation quickly and save time. And of course, bring it in 3D models of different elements, objects, vehicles, et cetera, is important. So we're going to start with our first poll. So let's give it a sec here. So I'll read it while you answer. Which off-highway application area are you most interested in? So we have agriculture, construction, mining, military, or other. What is your level of experience in simulating autonomous vehicles? None, beginner, intermediate, or expert. So we'll just give it another 10 to 15 seconds. And this will help us determine future content that we'll deliver to you like that. We're making sure to answer your needs best. Okay. So I guess we don't see the results. Oh, there they are. All right. So mining was number 1, followed by agriculture and other, and then military. So no construction in that poll. And then finally, as far as the experience, nearly 40% have never simulated autonomous vehicles, 50% are beginner, and 13% are intermediate. So thank you for sharing. Okay, so now we're gonna go over an overview of 40B Sim. So 40B Sim is a real-time 3D simulation environment, not just for autonomous vehicles, it's also used in robotics. This software was created by 4D Virtualize, and we are bringing it to market, and we work directly with 4D. 40B Sim user. 40B Sim users include Safran, Nexter, companies like AGCO, Michelin, institutions like Institut Pascal. So there is a mix of people using this, not just in defense, but also in research and agriculture. We also have users in road vehicles, but today we're going to focus more on off-highway. So as I just mentioned, we hit several sectors and applications with that. But one thing you may not know, and we're not going to go into detail in this presentation, is you can also simulate UAVs as part of not just a UAV only simulation, but you could also simulate UAVs interacting with other vehicles and robots in the field. And there's also the ability to simulate smart cities. So you can simulate communication between vehicles. The framework looks as such. It all starts with a simulator. So this isn't, if you're an OPAL-RT client, a regular simulator with analog input and output and digital input and output. This is more like a gaming computer with a powerful GPU to be able to render the 3D simulation and simulate sensors. Within the 3D simulation, we have our system, the autonomous system, whether it's a car, a tractor, robot, you name it. And then the environment, which we can model with 3D objects. And you'll see during the demo what we have to offer out of the box. And then finally, we simulate sensors. That's all made so that we can connect software in the loop, hardware in the loop, models in the loop, to be able to output that data to that software and then receive commands back into the simulation to control the autonomous system. What we also have is the ability to connect actual hardware. So we have a product that will be launched in this year, which will allow you to take signals from the simulation, whether that's camera or LiDAR, and then inject it directly into an ECU. So that's what we would call sensor hardware in the loop. I mentioned sensors. So simulating different types of sensors is very important because there's a lot of fusion that can be done with these applications. So we offer cameras of different types, GNSS simulation, we have LiDAR, both 2D and 3D, we have IMUs. We also have models that have been developed based on industry products. So for example, from Velodyne, SICK, Ooster, as you can see below. I talked earlier about ground truth. So on the left, you have RGB fisheye cameras and omnidirectional cameras. On the right, these are ground truth cameras. So these cameras are then used to, for example, generate synthetic data for machine learning algorithms. So we can annotate data based on the semantic camera. So these are all available in 4D vSim. And finally, what does that actually look like as an overall flow? So you can import, as I mentioned, 3D models, CAD models, GIS, so terrain. We can co-simulate with MATLAB, with ROS, other software. And then finally, we can interface either with software in the loop, models in the loop, which I'll go over briefly, or real embedded systems, or finally take data and output it to share for your own applications that don't involve simulation. So whether it's training machine learning algorithms or another application. So let's talk about applications. In brief, so there's two main concepts. There's applications where, and we're talking about real-time applications here, where we simulate everything together. So the software that we're testing, the algorithms that we want to test, they're all simulated together. So we can do that in two ways. We can do it as a model in the loop or a software in the loop. The key difference here is that a model in the loop may not be the final production code that you want to actually implement in your product. So it may be a MATLAB Simulink simulation that's connected directly to the simulation, versus software is an actual program that's been compiled and is connected to the simulation. For Hill, we're talking more about real hardware. So maybe you have, as I mentioned previously, an ECU that you want to connect to the simulation. That's Hill. Digital twins. So here's an example with 4D vSim where we have a pedestrian crossing a street. And you can see the pedestrian crosses. And in real life, here on the bottom left, this car, which is marked in red, stops. You may note there's no car in the middle here. So what's happening here is we're actually representing digitally the real life scenario and connecting it to the simulation so that we can actually create an augmented digital twin scenario. So this is a real-time application. Of course, you can create a digital twin that doesn't connect to real devices in the field, but this is the kind of capability that you have. Finally, driver in the loop. So for driver in the loop, we have two main application areas, or I should say ways to connect to the simulation. You have the ability to connect a steering wheel and chair and monitors of different types. You can make this huge, or you could also connect a VR headset. Now, I'm not going to go into the details, but this is a hot research topic in the sense that you can observe human behavior, understand their interaction with the autonomous vehicle or machine. data generation for AI and machine learning. So there's been research on this because obviously using real world data is ideally the best way to train a machine learning algorithm. But simulation generated data has also been shown to be an effective complement to real world data. So there's a lot of value in being able to bring in synthetic data that you may not be able to obtain from actual real world testing. Or maybe you're not permitted to do that type of testing. There might be a host of different reasons why you cannot actually obtain that data. So with 4D vSim, you can generate that type of data. So whether it's LiDAR, camera, or other sensor data. And as I mentioned, you can also annotate that data. So for example, here, we can annotate humans and forklifts. We could also annotate other objects. It's configurable. And in this one here, this is more of a robotic agriculture or horticulture application. We're detecting strawberries, but you'll note, it might be hard to read, you can actually see the different maturity of the strawberries. So white and French and mature. And then finally, just in a bit more detail, ECUs. So I mentioned hardware in the loop. How do you connect hardware in the loop? Now, it's not just a question of outputting a signal from a simulation. You need to process that signal. And in fact, what we can do is also modify the signal. We can adjust the contrast. We can add noise. We can shift the image. We can overlay the image with dust, with rain. We can basically merge images directly on the product and then send that via an industry standard protocol to the ECU. The other thing that we can do is also simulate the rest bus. So like that, you can create a very comprehensive hardware in the loop simulation. Oh, so just some project examples before we launch to our demo. So the first one is we're talking about INRAE or INRAE. So this is a research institute or university in France, which uses 4D vSim for several projects. So one of them you can see here is just a farming simulator. So being able to simulate how it is to operate farming equipment on a farm. But one that's I'd say more interesting is they actually have scenarios that they use for the validation of agricultural robotics. So they have effectively a virtual testbed where people can bring their algorithms and validate whether they actually function the way they should, which is obviously not always simple in the field. Finally, there's military projects. So PSD Furious was a big one involving Safran and different participants and partners, and even including the French military defense. So the whole idea there was to bring in 4 different types of autonomous systems. So you'll see here, this is the real life dune buggy. And then on the right, we have the simulated one. And then there was also robotic systems, so unmanned systems, such as this mini Rex. And we were also simulating UAVs. So you can create some pretty detailed simulations based off that. And another one also involving military is iMugs. So iMugs was a project involving many participants, several countries in the European Union. And it was, the objective of the project was to build and demonstrate a system of unmanned ground and airborne vehicles that can perform a variety of surveillance and rescue tasks. So the idea there was to really make it so that all these unmanned vehicles could synchronize and communicate and work together. So to our second poll. So it's a question involving what kind of work you do. So which application best fits your work? Perception, sensor fusion, planning, navigation, control manipulation. You can select all of the above or none of the above. So we'll give you about 20 seconds to answer that. And Next up, we're going to have our demonstration with Valentin. So we're going to see the results. Ooh, all of the above, by far the winner. And we do have some folks that are more focused on specific applications. All right, so we're going to switch over to Valentin, and I'm going to stop sharing.
Thank you, Tom, for your presentation. Again, my name is Valentin Puyfourcat, and I'm a field application engineer at OPAL-RT. And today I'm going to be covering the 4DV demos. So for the demo, we're going to talk about the three software that compose 4DV Sim, which are the editor, the software you see right now that lets you edit your simulation scenario. We'll have the 4DV monitor. This tool lets you observe the sensor outputs and other data that you want to send from the simulation to a viewing tool. And finally, the system designer. This tool lets you create and import, more importantly, your own 3D models of objects and vehicles, robots, and lets you configure them. Okay, so let's jump into the 4DV editor. So this is the graphical user interface for the editor. This is the main way that you will edit your simulation. And as you can see, there's two main views over here. They correspond one to another. The 3D view over here lets you well place roughly your objects to in the vicinity where you want them. Lets you edit the settings on the right side for each object, while the graph view lets you it lets you edit the settings as well, but it allows you to connect the different blocks together. And for each object in the simulation, you'll have a functional block. For example, for a robot, you would have inputs such as speed and steering, and the output could be the position of the robots, the angle of a joint, or things like that. So these signals then you can route any way you want. You can send them out through our communication interfaces. You can receive data from those interfaces and put them into the different blocks. Over here, for example, we have a plugin code that is a way to interact with the simulation using a C++ API. So I'm inputting some data, playing with it, and outputting it, for example, to this robot over here, and we'll see that this robot is this one in the simulation. And so this way I can control my robotic arm, for example. So this is in a sense what's going on here. But now let's talk more of what's available out of the box in the 4DV editor. So first thing first is the environment. Right now we have a farming environment. Out of the box we have a few maps. We have canyon, desert, some more sandy environments. We have indoor environments, as well as urban environments, like Lyon, a city in France. And this map is Montauldre 2, another city in France, which is a farming environment. Out of the box, we have a few 3D objects that you can use to embellish a little bit your simulation scenario. What does it have? Bushes, trees, different pallets and boxes and walls, things like that you might find useful depending on your application. We have models for humans and for cars. These cars can be controlled just like any other robot, by the way, but this is more urban vehicles. We can play with the weather. That's the most useful thing. I think in these disturbances, the ability to add rain, fog, and snow, which will impact the reading of the sensors. So that's available out of the box and could be changed at runtime. So that's all quite useful. Out of the box, we also have mobile robots. These robots, like the mini Rex over here, which I have on the ground. So this one is more of a tank mode with the chains over here. there's also Ackerman controlled robots with front and rear steering. Really, all these basic types of robots are available. You see over here Pasejka. So this refers to a specific tire model, a widely used tire model, which models properly the deformation of that tire, and so that is really useful when dealing with off-road simulation. And in addition, you have control over the parameters of this model, so you can really go deep into the tuning and the accuracy of your simulation. Out of the box, okay, sensors. Yes, Tom has covered the types of sensors that we have already. I'll just go over them quickly. So for the cameras, you have multiple types of cameras: the infrared cameras, depth, semantic cameras to create ground truth. We also have just simply RGB cameras, 3D cameras, all that sort of stuff. And we have added a few in this project. I'll show you in just a second. In terms of IMUs, we have multiple models as well. These models have been configured to match the readings of these vendor parts, and that's true for many of the sensors over here. For the GPS, so the GPS works essentially by setting the time and the location of the simulation relative to the real world, and the constellation will update based on those inputs. So if I just go quickly over here, we can set a set time and location for the simulation, and that will affect the readings of the GPS sensors. What else do we have? An ultrasound for ranging, LiDAR, 2D and 3D LiDARs. So the LiDAR, same. We have some SICK LiDARs. These models already configured to match their real counterparts. Very well. Let's move on to actuators. So actually, now that we've gone through these few tabs, I think it shows the flow of someone designing their own simulation. We would start with an environment, place our props. We can maybe place a robot that suits your needs. To the robot, you can add sensors. So let's add a 2D LiDAR. This R2000 over here. There we go. The LiDAR is in the simulation, and over here. There we go. The only thing next is to place it relative to a robot. So what I'm going to do is I'm going to go to the Mini-Rex. Mini-Rex over here. If I zero it on the Mini-Rex, oops, okay, focus, there we go. We zeroed it on the Mini-Rex. Let's say I want it over here. The next thing you would do is tell the simulation that you want these two 3D objects to be one, and so that's when you add a joint, a physical connection between two entities. In this case, we would use a fixed joint. We specify the two elements. So in this case, it will be, this is the sensor that we added. No, this was a LiDAR, R2000 to the Mini-Rex. Mini-Rex, press OK, and now as we move the Mini-Rex, the other LiDAR will follow, and in fact during the simulation these multiple objects are considered one. Now in the case of this robot, I had already added a 2D LiDAR in the front over here. I'm just going to delete this one. There we go. Okay, perfect. So now we've added the robot, we've added sensors to them, we have fixed them in space so they don't just go fly around. Another thing that we might want to do is add connectivity. So in the I/O tab under interfaces, we see that we have multiple types of connection. So of course we have Ethernet-based connection if you want to send your data through TCP. We have ROS connection. So With ROS, you can send point clouds, your images, and joint states, all that sort of things. With file and multi-file, you can record very easily your camera outputs, and you can save into any type of file with any type of extension. So it's really flexible. And to show you maybe a couple examples, so they're in yellow over here in my graph view. If I go on this one, we see that there's a TCP connection with the port 3010, and what I'm doing is I am sending some LiDAR value. It looks like, yeah, the SICK LiDAR over here. I'm sending these values to TCP. So this is a connection actually to the 4DV monitor, which we'll see in just 1 second. And at the same time, we see that this same SICK LiDAR I am sending to ROS. I am sending the laser scan through ROS. And so you will be able to take a look at this data using something like RVs to if you don't know what that tool is, it's a simple tool that comes with ROS that lets you visualize any type of data, camera data, point cloud data. And so we'll see if I can get that running. Well, actually, it looks like my simulation is running. And this is the point clouds going on right now, the 2D scan of that sensor. Okay. So let's have a look at the simulation because it has been running. Up. This is the second robot. The mini Rex over here. Let's have a look. Up. Right now it's turning around. Okay. There we go. We have the corresponding data here. Up as it's entering the greenhouse. It's seeing the different plants over here, the crates in the center. It's relatively low compared to the ground. But yeah, this is, it looks like it's mirrored actually. Up, like this. Yeah. Okay, so now let's take a look at the 4DV monitor. We should be able to see very similar data. Okay, 4DV monitor. So this is the 4DV monitor. This project I have already made and configured for the simulation that is going on right now. I'll show you briefly how it's done starting from scratch. Okay, so this is another application, the 4DV monitor. Let's create a new project over here, and it's very simple. It's again using the GUI up here on the online library, or sorry, the library. It's a series of widgets that corresponds to the different sensors, and will let you visualize them properly, as well as charts if you want to plot anything, the position of your robot or your joints in space. It's really up to you. So for example, we select a camera, we add a source. So this 4DV monitor works through TCP. So in the editor, you'll have to set up some TCP connection like I did over here. And for each sensor that you want, you'll have to give it a specific port and match that port in the 4DV monitor. Now, there's a simpler way to do this, is to use the online library. Click connect over here, and then you'll have a list of all the data that was made available in that simulation. You can add them. For example, let's have a look at the 3010 generic LiDAR over here. Press OK. Press yes. Support the camera. Yep. 3010. Up. There we go. Okay. So right now we can see the mini Rex flowing through, going through the greenhouse, which should match the data that we see in RVs. There we go. Perfect. And so now to have a look at everything in that simulation, let me open the other project that I have over here. Okay, so now we can have a look at there we go, the LiDAR, the 3D LiDAR output of the main tractor that I talked about earlier. We can see the two feeds for the fisheye cameras on the side. And yeah, this is the kind of data that is generated right now in the simulation. Now let's have a look at the other sensors. We have the stereo camera in the front right here. We have the two IMUs at the bottom here. We see that there's a difference in scale between the two, and the constellation over here for the GPS sensor. There we go. And we can have a look at the Mini-Rex. We have the LiDAR over here configured, and a semantic camera here that is set to follow the robot in this sort of cinematic way. And here you could see that it is possible to annotate the data. Right now it's simply semantically annotated. There's no bounding boxes or anything, but this is already something that you can do. Okay, let's sorry about that. Let's stop this monitor. Okay, and finally let's jump to the 4DV system designer. Okay, so the designer is used to, again, import or create your own 3D models that you want to have in your simulation. Now, one thing I wanted to show you is the basic, the template vehicle that comes with 4DV that lets you then easily modify it, and just to have a look at the kind of options and settings that we have. So you see I already created it. I'm going to create a new one. I'm going to use vehicle template, press enter. Okay, so one thing I haven't mentioned is the meshes for your vehicles. So as you can see here for the tires, the mesh, the series of surfaces that define the tire in this 3D world is quite well defined. If you compare it to the vehicle itself, where we see it's rough boxes, rough shapes. And so the reason for that is that we want to have great accuracy, and it's important to understand how the tire is contacting the ground. And so by having that many meshes or a very well-defined mesh, we can know pretty accurately what's going on, and that paired with a good tire model, we can have a accurate simulation. Now for the body, it's less important. There's less need for contact over here, and so this is why the mesh is relatively simpler. Now this system designer also comes with the two views, the 3D view as well as the graph view. In the graph view, what I wanted to show you is the series of actors and joints that compose essentially the transmission, or the connection between the body and all the way to the wheel. So first we have an actor for the wheel, where the meshes are defined. To that we connect different joints. For example, this motor joint is connected directly to the wheel. Oops. Okay. For that motor joint, we have control over the maximum torque and other kinds of parameters that might be useful in defining the kind of behavior you want for your vehicle. Same for the direction as well. So there's one joint for the motor, one joint for the direction turning, and that also can be tuned in the very same way. Although it's the same type of joint, the values will be different. Finally, we have the suspension. So here we have control over the damping and spring parameters, and so that you can define and customize for your own needs. Furthermore, what do we have over here? So this vehicle actuator lets you have essentially information on the state of the robot internally in terms of the physics being calculated, and so that is an option for you to have during the simulation available. If you need that for some type of control, this information is available. And similarly to the 4DV editor, we have a few tabs on top, and so these are to create new actors, new geometries, new objects. So if you are trying to model your own robot, you will have likely a visual and the physics meshes just like this, but there might be things that need to be added or modified, and so you can do it from the 4DV system designer directly. Same to create joints. If you have so if you're creating your own robotic arm, you will have to create the different joints depending on what's on the shape of your robot. You have the possibility to integrate the sensors right away from here in a vehicle, in a robot, and you can do this. It's available. I would say that it makes more sense to use those available in the editor, because you might want to move your sensors and change their resolution, change their settings, things like that, and it's a little less convenient to do it from over here, from the system designer, because you have to import back and forth your model from the designer to the editor. Just a thought right now, but it's available here for you as well. Okay, I think that covers it. That covers it for the system designer. So I just want to thank you for your time, and we'll have questions, time for questions in just a second. Back to you, Tom.
Oh, that was great. Thank you, Valentin. So I'm just going to share my screen again. All right. So, well, number one, thank you so much for listening to us, and we're going to answer some questions. If you have any that you want to send over to us, well, you can send them now, or following the webinar, you can contact myself and Valentin, or find us on LinkedIn, whatever works. If you're already an existing OPAL-RT client, you can contact your account manager as well. So let's start. So we have a couple of questions about the system. So is this 4DV part of the OPAL system, or is it standalone? It is standalone. So 4DV Sim is not like OPAL-RT's other products. It is, as I mentioned, it runs on a computer that has a GPU. So you don't need digital or analog IO like you do for more on the power system side of things, which is the other market, or one of the markets we cover. And then a follow-up to that question is it used as modeled in the loop? So if you were to use the OPAL-RT system, say you already have one, and you wanted to connect it to this sort of simulation, you could connect it as a controller, of course. So you could send signals from the OPAL-RT system that you already have. So and send the controls over to the 4DV Sim. You could also simulate, say you already have the capability to simulate electric motors, BMS, batteries. You could connect the two as a co-simulation. So as I mentioned earlier, you have that connectivity option. Here's another question. Is it possible to learn this tool? So, that's something I should mention. We didn't really talk much about it, but we do have, so for example, say you're interested in this and you're like, I don't necessarily have the capability or the knowledge or skill set currently to set this up. We do have resources at OPAL-RT. So we have staff members who can help you on site remotely. We do offer training, of course, with that product. So you just need to get in touch with us, and we're glad to talk more about that. Someone asked us, is this available in India? Yes, it's available internationally. You can, you just need to speak to us. And we have we're almost done here. So thank you for those questions. Yeah, so if you do have anything else, just reach out, don't be shy, and thank you so much for joining us today. And oh, can 4DV be interfaced with OPAL-RT electric vehicle models? Yes, it can. So we can connect OPAL-RT electric vehicle models and 4D vSIM using different protocols. So we have CAN bus, TCP/IP as options, and who knows, we may need to develop more down the road. So, well, that's it. Thank you so much, and have a great day.